So this is a question that is going to require you to find concentrations at equilibrium. So obviously every time we see a question like this, we're going to want to use an ICE table. So I'll read you the conditions that we're going to start with. If a reaction mixture initially contains 0.175 molar SO2Cl2 and no other substances, find all equilibrium concentrations. And we know that the K sub C for this reaction is 3.00 times 10 to the negative 7. So to solve this, first we need to talk about what our initial concentrations are. And those are given in the problem. So we know that we start with 0.175 molar SO2Cl2. And we know that there are no other substances in our flask, so we're going to put zeros here because there's nothing else except SO2Cl2. So now we need to talk about the change to equilibrium. So as this system shifts, some of this reactant is going to be used up to make product. So this is going to go negative X because it's being used up to make products. And these are going to be just by X. And the reason why we're using just X with no coefficient in front of it is because our equation is balanced without any coefficients. Now we need to establish what the equilibrium is going to be. So if we start with this molarity and change it by a factor of X, we can express our equilibrium as 0.175 molar minus X. And our equilibrium in these two species could be just expressed as X because they started at 0 and they changed by positive X. Okay, so now if we want to solve for X, all we need to do is write an expression to relate K sub C to concentrations. So we can say K is equal to the concentration of SO2, our product, one of our products, times the concentration of Cl2, our other product, divided by concentration of our reactant, SO2Cl2. Now notice these are all gaseous, which means they factor into our equilibrium equation. And once again, none of them have coefficients, therefore all of these are just raised to the power 1. So now that we have this, we can say that this whole equation is equal to our K sub C, which is 3.00 times 10 to the negative 7. So now we can simply plug in these values for our concentrations and set them equal to this. So we'll say 3.00 times 10 to the negative 7 is equal to the concentration of SO2, which we know is X, times the concentration of Cl2, which we know is X, all over the concentration of SO2Cl2, which is 0.175 minus X. Okay, so now there are two different methods that you can take to solving this problem. So we can do X equals small, or we can figure out the quadratic equation. So first, I'm going to talk about how you do X equals small. So you can use X equals small when there's a big difference in magnitude between your K sub C and your concentration. And the reason why you can do this is because this K sub C is very small, so it's telling us that at equilibrium, this reaction favors products a lot. So that means if we change our concentration of products by some very small number X, by sig figs, it's not going to change at all. So we can ignore any number X that is subtracted from a molarity. So if we say X equals small, we can essentially ignore this X right here and rewrite this expression as 3.00 times 10 to the negative 7 is equal to X squared, I just multiplied those, over 0.175 because we're ignoring that little X. So I'm going to write over here X equals small approximation. Okay, so now this is simple. All you have to do is multiply this 0.175 by this and take the square root, and that gives you X is equal to 2.29 times 10 to the negative 4. So we can see, just by looking at that X is very small in this case, which would make us think that we're probably right. But if you do X equals small, you have to justify it. And the way that you justify it is by saying your X value divided by the initial concentration that you started with. This is just a way to make a ratio to determine how different your X is from your original concentration. So what we're going to set up is 2.29 times 10 to the negative 4 divided by 0.175. And we're going to multiply that by 100 so that we can convert it into a percent. And as long as this percent is less than 5, then that means that our x equals small approximation is good. And when you calculate this, you turn up to get 0.1309%, which is definitely smaller than 5%. So that means our x equals small worked. That's good. So now I want to show you the other way you can calculate your x here before we plug everything back in and get our final answer. So the other way would be to do quadratic. Okay, so if you want to solve the quadratic formula for this part right here, what you're going to have to do is get all of your variables on one side. So if you start to do that, I'm going to multiply things out and skip a few steps because it takes quite a while and it's going to take up a lot of room. So I'm going to skip a few steps of just simple algebra and start at 5.25 times 10 to the negative 8 minus 3.00 times 10 to the negative 7 x minus x squared equals 0. And then this can be rewritten with positive signs if you switch the sign of everything. So that's going to be x squared plus 3.00 times 10 to the negative 7x minus 5.25 times 10 to the negative 8 equals 0. Okay, so now we have an A, B, and a C. And we know that if we have this form where we have x squared x and nothing, we can plug all of this into the quadratic equation, which is, I'll write it right here, x equals opposite b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so if we plug that, these numbers that we have in right here, we get x equals opposite b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so now this is pretty simple to see. I'm going to have to skip a few steps in the essence of space. So what you would do is you would multiply all these three terms by each other, and you would square this, and then you can subtract those two numbers. So I'll skip to that next step. Plus or minus. So if we add or subtract these two numbers, then we end up with 2.1 times 10 to the negative 7. And we're dividing this all by 2 because that's just 2 times 1. And then from there, if you take the square root of this number, you will get x equals negative 3.00 times 10 to the negative 7 plus or minus 4.58 times 10 to the negative 9 over 2. Okay, and then from there you have to do this plus 4.58 times 10 to the negative 9 divided by 2 and minus. So I'll write both of those down here. Divided by 2. This is the exact same thing except with a minus instead. Minus by 2. Okay, so for this situation, x equals 2.289 times 10 to the negative 4. And in this situation, x equals negative 2.289 times 10 to the negative 4. Okay, so we do get two answers because obviously this is a squared function, but we know that we want x to be positive because we've already taken care of our signs up here. So we're going to say that's not the answer that we want. This is the answer that we want. And we can compare it to what we got with x equals small, and we see that they're almost identical, and if you went off of sig figs, they would be. So I'm going to go ahead and erase what I did on the quadratic so we have room to solve the rest of the problem. But I want you to know that you can use the quadratic equation every single time, and it will work. But it does take a little bit of time, and you probably won't have time to do that on your test. So I would suggest getting really comfortable using x equals small, because you can get definitely the right answer much faster that way. So now that we have x, we're trying to figure out all equilibrium concentrations. So all we have to do is find our equilibrium concentrations by plugging in x into these three terms that we have here. So to find the concentration of SO2, Cl2, all we have to do is say 0.175 molar minus our x, which is right here, 2.29 times 10 to the negative 4. You'll get 0.17477, which is approximately equal to 0.175 by sig figs, which means that our x equals small was definitely the right thing to do. Now if you look at the concentrations of SO2, that's just going to be 2.29 times 10 to the negative 4 m. That is also a molarity, because it's just x. And the same thing for chloride. Now, I know that these seem like very small molarities, but if we take a look at our K sub C, we can see that in this reaction at equilibrium, reactants are greatly favored over products. So it makes sense that we would have much more reactant than product based on this K sub C.